Hello trigonometry students, my name is Jami Emigh and we are going to start our fourth video for chapter 1. Okay, we left off on this table right here titled Function Values of Quadrantal and Special Angles Using the Table, and what we're going to move to now is the graph of sine. So we're going to use the values on the table to help us graph sine. Okay, I want you to focus on the degrees right here. So we're going to use degrees as one of our axes. This is actually going to be the x-axis. And these ones are all of the quadrantal angles and all of those special angles, 30, 45, 60, and their multiples through the quadrants. And the values of sine of theta, that comes from this part of the table. So these are going to go on the y-axis of our graph. Okay, so I'm going to go to the next slide, but then I'm going to come back to this one. I just want to show you what it's going to look like. On the next slide here, we've got the x-axis, which are the angle measures of theta. You can see those are all filled in for us. But notice that this second row, the y-axis or the values of sine theta, is left blank. So I'm going to have to look back at the table and fill all of these in from the table. And that could take me some time if I have to toggle back and forth between slides. You have yours printed or on a device that you're annotating on, so it's not as difficult for you, but I think this is going to be something useful you're going to want to follow along with. So let's pretend we have to fill this row in right here by just looking at the table one time. Okay, so let's give it a try. I see a 0, I see 1/2, rad 2 over 2, rad 3 over 2, and then I see a 1. Okay, not so sure about memorizing that yet, but I'll give you some ideas on how to. On the other side of 1, I see a radical 3 over 2, a radical 2 over 2, 1/2, and then a 0 again. All right, I picked up on a couple of patterns. The first one is that I saw 0, 3 values, 1, 3 values, and back to 0. Okay, so now if I can just focus on these 3 values, well, I see a pattern here as well. All of them are over 2, so that's helpful. And then I see a 1, radical 2, radical 3. I'm actually going to add the radical over the 1. That is completely legal because the square root of 1 is 1. But the reason I'm doing it is because now I can see a more distinct pattern. It's radical 1, half of it, radical 2, half of that, radical 3, half of that. And then on the other side of 1, it repeats, but it's the reflection. Rad 3 over 2, rad 2 over 2, and radical 1 over 2. Okay, I think I got that. I think I can memorize that now, just picking up on those patterns. Let's go see if we can do the rest. On the other side of 0, I notice we're back to 1/2, but it's negative. Back to rad 2 over 2, but it's negative. Back to rad 3 over 2, but it's negative, and then drops down to -1. And on the other side of it, rad 3, negative radical 3 over 2, negative radical 2 over 2, negative 1/2, and that would bring us back to 0. I'm going to add a 0 down here, just so I can see it in its entirety, okay? All right, so the 2 patterns I picked up on from there are, I start at 0 once again, and I have 3 values, 1, 2, 3, that bring me to -1, and then 3 values, 1, 2, 3, that bring me to 0. Okay, I think if I add this radical over the 1 just like before, it will make my pattern stand out even more. Let's see if we can fill in the row on this table with those values. Okay, here we go. We said 0, 3 values, 1, 3 values, 0. The 3 values right here, they're all positive, okay? All of this is positive. So the first one is radical 1 over 2. You can just write 1/2 if you want. I just want to show the pattern. Then radical 2 over 2. then radical 3 over 2, and now 1, and the reflection on the other side of 1. Radical 3 over 2, radical 2 over 2, and radical 1 over 2, which again, you're welcome to write just 1/2. All right, that's a lot. We're over halfway done, and let's see if we can get the rest. Okay, we know it's 0, 3 values, and it was -1 this time. 3 values, and then it would bring us back to 0, or 360 degrees. I'll put the 0 here too, just to show it completely. Okay, so we're going from 0, decreasing to -1. So that would be the -1/2 first, followed by negative radical 2 over 2, negative radical 3 over 2. We get to the -1, and then it's the mirror image. So this one reflects to here, negative radical 3 over 2, followed by negative radical 2 over 2, and last is -1/2. We did it. Okay, so we have a good way. Hopefully you picked up on that, and you can also memorize these ones here. If you memorize the second row like this for sine and cosine, we saw in the last video that will lead you to the values of tangent, cotangent, cosecant, and secant. So if you're thinking to yourself like, well, this is going to be a lot to memorize, that's not the case, okay? Memorizing this pattern right here, and then the cosine pattern, which we'll do on the next slide, all of that will lead you to the others. So there is a bit to memorize, but it's going to be useful to you to memorize that stuff, not just for your exam, but you want to be able to quickly reference. Let's say you see sine of 90 degrees. If you see sine of 90 degrees, you're going to want to quickly reference that value is 1. So let's take these values and put them on our graph. We have our horizontal axis, or our x-axis, and we've got the quadrantal angles and special angles. Quadrantal angle 90, 3 special angles, quadrantal angle 180, and so on. And then on our y-axis, the vertical axis, we have the radical 1 over 2, which is equivalent to 0.5. I'm putting them in decimal form just so you can see, or hopefully you can better see how we're increasing from 0 up to +1. Radical 2 over 2, if you type that in your calculator and round to the nearest tenth, it's approximately 0.7. So hopefully you can see that is above. Radical 2 over 2 is greater than radical 1 over 2. So the graph's going to get higher right there. Radical 3 over 2 is actually even larger than that. If you typed in your calculator and round to the nearest hundredth, it's 0.87. And then 1 is higher than that. And it's the same in the opposite direction. Negative radical 1 over 2 is equal to negative 0.5. Negative rad 2 over 2 is a value less than that, so further away from 0, it's approximately negative 0.7. And negative radical 3 over 2 is a value smaller than that even, so further away from 0, it's negative 0.87. And drops us down to our minimum of -1. Okay, let's start plotting some points. First one is 0 degrees, outputs a value of 0. So sine of 0 degrees equals 0 would go right here. Next one, 30 degrees is, let's go to 30 on the x-axis, and we'll get to put a point at the value 0.5, or 1/2. Next is 45 degrees. Value is rad 2 over 2, which is approximately 0.7. Next special angle, 60 degrees, has a value of radical 3 over 2, which is approximately 0.87. 90 degrees now has a value of 1. And on the other side of 90 degrees, it's going to start decreasing. Remember that pattern? 0 to 1, and then decreases back to 0. So at special angle 120, we have a height of rad 3 over 2. At special angle 135, we have a height of approximately 0.7, or rad 2 over 2. And at 150, we have a height of 1/2. 180, value is 0. Okay? Now, we have plotted points for the special angles and the quadrantal angles, but there are infinitely many points between these that would create the sine function. And if you continued to, maybe you could use a calculator if you want to put more points before you do the connecting the dots. You could type in sine of 15 degrees, find the height, sine of, let's say, 75 degrees, find the height, and you'll soon see if we plot more and more and more points representing the value of sine, oops, it's actually going to make a smooth curve. Whoa, this is really hard to connect using my mouse, sorry. Gotta go up like this, so my points are not very accurate, but mine looked almost more like a V, but it should be a parabola. Okay, there we go. That will have to do. When I'm done with this slide, I'll erase all my work with my pen and show you the actual graph computer generated. Okay, so we've got sine in quadrant 1, sine in quadrant 2, increases in quad 1, decreases in quadrant 2. Let's see what happens in quadrant 3. At the value of 210, we drop down to, at the angle 210 degrees, we drop down to a value of -1/2. At the angle 225 degrees, we drop down to approximately -0.7. 240 is at approximately -0.87. 270 gets to the minimum of -1. On the other side, mine looks like a V again, but I know it's supposed to be a smooth curve. My axes must not be to scale. I created these by hand here, so it's not perfectly to scale, it appears. All right, special angle of 300 degrees has a value of -rad 3 over 2. 15 degrees is approximately -0.7. 330 degrees, if that were our theta, sine of that would be -1/2. And then 360 degrees bring us back to a value of 0. So connecting these with a smooth curve, not necessarily hitting all my points because I know sine is supposed to be a smooth curve, not a V. And there we have what is called one cycle or one period of the sine function. Sine is a periodic function, so this would continue. Right here, where we have this one cycle, this is one time around the unit circle, if you're using that tool. That's one cycle of sine, one period, but it continues in both directions, actually. It would do the same thing, follow the same behavior over here, dropping to a minimum of -1, and it would do the same thing if we continued in this direction, increasing to a positive value, maxing out at +1. And now I'll show you the computer-generated graphics here. There are our values. We got them all right. And here is our graph of y equals sine of x. Let's address the domain before we move on to the next slide. The domain is the set of x values in which this function exists. And I can see no holes, no jumps, no asymptotes or discontinuity along this x-axis. And if we continued in this direction as well as in this direction, we would find the same thing. Sine, the x values of sine, exist everywhere. So that would make the domain of sine of x all real numbers. We could also look at the range if we'd like. The range is all y values in which the graph exists. So up here at 1, it exists because it is a filled in circle or solid line right there. And it exists everywhere between +1. At -1, it still exists. You can see here, it exists. Solid line, filled in circle. But above and below 1 and -1, the graph does not exist. So what that means is that our range goes from -1 to +1. So let's just write it in interval notation. The range would be starting the interval at starting the interval at -1, ending the interval at +1, and it includes these values, so we use brackets. All right, next slide. We're going to do the same thing with cosine of x. So let's go back to the table and see if we can come up with some way to memorize the values for this second row here, the exact values of cosine of x. All right, so we need to challenge ourselves, see if we can memorize this column in one shot, so we don't have to toggle back and forth and back and forth. Okay, so this one starts at 1, all right? And then we see that it drops in value, rad 3 over 2, rad 2 over 2. I'm going to go rad 1 over 2, decreases all the way to 0, okay? Then on the other side, it's the mirror image, but it becomes negative, okay? Reflection but negative, reflection there but negative, and it drops to -1. All right, I'm going to pause there for a second, make sure I pick up on this pattern. So it started with +1, 3 values, 0, 3 values, and then decreased to -1. So everything from here to here is decreasing. So it goes from 1 to 0 to -1. That's going to help me remember that these 3 values in between go positive, and then once I hit 0, they've got to become negative to get us down to -1. Okay, I think I can remember that. Let's check the other side of -1. We start to increase negative rad 3 over 2. It's just the mirror image here, so this will be nice. Increase back to 0, and then it continues to increase. Let's add those radicals. Then it continues to increase, rad 1 over 2, rad 3 over 2, rad 2 over 2, rad 3 over 2, and after that it would circle back to 360 degrees or 0 degrees, which is 1. I'm going to go ahead and write that down here just so we can see it. All right, here we go. 1, 3 values, 0, 3 values, -1. 3 values, 0, 3 values, back to +1. I'll just write it here. Okay, so now I just got to get, we just need to get those 3 values filled in for each of these quadrants. Now to get from +1 to 0, we need to be decreasing in values. So we're going to go with our, well, you can see it here on the axis too. We're going to go with our rad 3 over 2, decrease to rad 2 over 2, decrease to rad 1 over 2. So that would be rad 3 over 2. Number smaller than that is rad 2 over 2. Smaller than that is 1/2. And that gets us to 0. Okay, then on the other side, we have to continue decreasing. So we have to get down to -1. So we're going to decrease to -1/2. Decrease again to a number smaller, which is negative rad 2 over 2. Decrease again to a number smaller than that, which is negative radical 3 over 2. Okay, next we need to get from -1 up to 0. So we need to be increasing this time. So we're down at -1. To increase from there, we need to have negative radical 3 over 2. So that's approximately negative 0.87. Then next would be negative rad 2 over 2, or approximately negative 0.7, followed by negative 1/2, which equals negative 0.5. And that brings us back, or down, no, up. That brings us from -1 up to 0. And from for our last three, we need to get from 0 back up to 1. So we need to be increasing here. So from 0 to 1, we'd be positive. So we've got radical 1 over 2. Increasing, so a number larger than that, rad 2 over 2. Increasing to rad 3 over 2. And then our 1 right there. Okay, hopefully you got that. Like I said before, it'll really pay off if you have these ones memorized for sine and cosine. The rest of them you can pretty quickly develop from sine and cosine. But being able to quickly reference, like, let's say you have a question where it's asking you what cosine of 90 degrees is equal to, you can go value of 0. That will come up a lot, so having these ones memorized for quick reference will pay off. Okay, let's graph this. Try to make it look a little more like a curve than those V's like last time, but okay, here we go. We've got 0, 1, 30 rad 3 over 2, 45 rad 2 over 2, 60, 0.5, 90 is 0, 120, we drop down into the negative range, negative 1/2, negative 0.7, negative 0.87, and negative 1. On the other side of negative 1, we increase, so we go back up to negative 0.87, up to negative 0.7, up to negative 0.5, and we're at 0. And continuing to increase, we're at 300 is 0.5. Cosine of 315 degrees is approximately 0.7. Exactly radical 2 over 2, approximately 0.7, okay? Cosine of 330 degrees is approximately 0.87. It's exactly radical 3 over 2. And cosine of 360 degrees gets us back to 1. Okay, so again, you can take your calculator out and come up with more points for any of these. And if you do so enough, you'll start to see that it is in fact a smooth curve that develops. Okay, so from the top, or from the start, it decreases, and it's actually concave down like this, crosses our x-axis, continues to decrease, but it changes concavity. We'll learn all about concavity in a future chapter. Then it minimums out right there and starts to increase, still concave up, crosses the x-axis where it changes concavity, but it continues to increase to there. Okay, cosine, y equals cosine x, is a periodic function. So what we have here is one time around the unit circle, but we know just like sine that if we were to continue in this direction, we would see it decrease. Look the same over here, and same thing over here. It would then decrease, and it would repeat itself over and over, and that is the graph of y equals cosine of x. So let me erase all of my annotation, and let's look at the computer typed up stuff. All right, there is our second row. We got all of those right, and here's our graph. Very nice. And let's talk about the domain. There is no place on the x-axis in which the graph does not exist. for example, if there was like an open hole or a break or a jump, it's not discontinuous anywhere on the x-axis. So it has the same domain that sine had, which is all real numbers. And it turns out it has the same range as sine as well, because on the y-axis, this graph exists from -1 up to +1, but it does not exist below -1 or above +1. So the range, let's go with interval notation again. Interval starts at -1, we use a comma. Interval stops at +1. Since it's including these, we use brackets, contrary to if it did not include them, it would be parentheses. All right, let's see what's next. Okay, here on this slide, we have the work that we did for the graph of sine. You can see it right here, hopefully. We're in function notation, so it's f of x equals sine of x here. And all the work that we did for cosine, we can see is right here. In function notation, f of x equals cosine x. Okay, so we took a lot of time and effort to graph that piece and this piece of these 6 graphs. So how can just those 2 pieces right there lead us to all this other stuff? Well, we saw that sine would, should we continue in this direction, it would have the same cycle. So this right here is a graph of 2 periods of sine. One, and now a second one. Same with cosine. We talked about if it were to continue in this direction, now we have a second period of cosine. So this right here is a graph of cosine, 2 of its periods, okay? Here is 1 cycle or period and 2. And it would continue, okay? These are just finite or snapshots of sine and cosine. All right, this slide is asking us what the range of each of these graphs are, which we figured out on the last 2 slides already. The range of sine is -1 to +1, and the range of cosine is also -1 to +1. Okay, let's use sine to lead us to its reciprocal function cosecant. I'm going to go ahead and add the graph of sine onto our graph of secant. Okay, there's 1 cycle of sine, and let me do the other one like this. Okay, now the sine function is the reciprocal function of the cosecant function. So what that means is wherever sine has a value of 0, in this example we can see that once, twice, 3, 4, and 5 times. At these 5 points, sine is equal to 0. So the reciprocal would be some value divided by 0, which is undefined. So for cosecant, at these same points, we have asymptotes. There is no defined value of cosecant at, this would be -360 degrees or -2 pi radians. And we'll talk about radians soon. Here, at sine value of 0, cosecant, its value would be undefined, dividing by 0. That's why you see an asymptote. Here, this is an asymptote as well. Just looks like a solid line because it is the y-axis. Here where sine is 0, cosecant is undefined. And here where sine is 0, cosecant is undefined. So we haven't found any points on cosecant yet, but we have found where it is undefined. Now let's try to find a few points on cosecant. All right, here sine equals +1. Well, the reciprocal of +1 is 1. So this point is also on cosecant. So we have found our first point on cosecant right there. Here's another one. Sine's value is 1, so cosecant's value is also 1 because it's the reciprocal. So we have found 2 points on cosecant. Let's go to these ones next. Here sine equals -1. Well, the reciprocal of -1 is -1. so cosecant also equals -1. And here, sine equals -1, so cosecant also equals -1. Okay, so for the cosecant curve, and those are the blue U's, okay? These 4 blue U's, those are the graph of the function f of x equals cosecant of x. So far, we have a lot of stuff written down, but we really only have 4 points on cosecant so far. 1, 2, 3, and 4. Okay, now let's add a few more. I'm going to go from the origin. I know here sine hits a point of 1/2 or 0.5. Thinking of it as a fraction, that would be 1/2. Well, the reciprocal of 1/2 is 2. So right here, when sine's value is 1/2, cosecant's value approaches or is 2. Let's go again. Sine is 1/2 again right here, so cosecant is 2. Let's go again. Sine is -1/2 right here. Well, the reciprocal of -1/2 is -2. So cosecant. Sine is -1/2 here, so cosecant is -2. Here, sine is -1/2, so cosecant is -2. Here, sine is -1/2, so cosecant is -2. Here, sine is +1/2, so cosecant is its reciprocal of 2. And here, sine is +1/2, so cosecant is its reciprocal of 2. Okay, I'm going to erase everything that is not actually a part of f of x equals cosecant x. So what I want to show you now is that this u right here, we talked about 3 specific points on it, but it would continue to increase towards positive infinity, but it would never pass or cross or touch the asymptote here. So it's a parabola. You guys have studied parabolas probably in your algebra courses or somewhere else. So cosecant actually continues to positive infinity and negative infinity there. Just remember that the graph will not touch or cross these asymptotes. And that's because these are vertical asymptotes. If you've studied horizontal or oblique asymptotes, it's a little different case. Sometimes those can be intercepted by the graph, but not vertical asymptotes. It will never, the function will never cross a vertical asymptote. And that is our graph of cosecant of x. We're being asked what the range is. Remember that the range is all values of y in which the graph exists. Well, on the y-axis, I see that it definitely exists at +1 and above +1. But notice there's this whole missing piece. This is where sine used to be, sketched at least. So as far as y values, cosecant doesn't exist between +1 and -1. However, it increases again, however, it starts to exist again at -1 and below, all the way down to negative infinity. So the range for this one is everywhere except +1 to -1. So in interval notation, we would write that as, starting down here, it exists from negative infinity to traveling through the interval to -1. We would use a bracket on the -1 and a parenthesis on negative infinity because that's a concept, not a value. Then there's this jump, so we would use the union symbol, and the graph starts to exist again at +1, so this is the next interval, and it continues all the way to positive infinity, which would be a parenthesis. So the range for cosecant in interval notation is here. All right, we'll try to go a little faster through these other ones. Sorry, that one took a long time to develop. Secant, I'm just going to sketch cosine here. in hopes that you can see that secant is the reciprocal function, just like cosecant was the reciprocal function of sine. So you can go through point by point, increase these asymptotes, increase these parabolas using the same method that we did over here, and that will lead us to the graph of secant. I'm going to erase cosine though, because I don't want you to accidentally think that that cosine graph right here is a part of secant. Secant graph is here. Okay, so this slide is again asking us for the range, and it's going to actually have the same range that cosecant did. And that is because the graph does not exist from +1 to -1, but it does exist at 1 up to infinity and at -1 down to -infinity. Okay, so that's 4. Now we have 2 more here. Noticing a couple things. Tangent increases as we travel from left to right. It does not exist at these asymptotes. Whereas cotangent, its reciprocal function, decreases as we travel from left to right and does not exist at these asymptotes. They're different asymptote values. Okay, this slide is asking us for the range though. Well, tangent, or the range, is wherever tangent exists along the y-axis. So there is no place on the y-axis where tangent does not exist. It exists way down here to -infinity, and it increases all the way through up to +infinity with no holes, no gaps, no discontinuity. So the range for tangent is all real numbers. Same thing for cotangent. The range, it increases, decreases to +infinity and -infinity, no holes, no gaps, so its range is all real numbers. All right, let's see what that looks like in a table here. So the ranges of trigonometric functions are, for sine and cosine, we know that it's -1 to +1 including, so we wrote it in interval notation. This is called set notation, so just another way to write it. This is read all y such that the absolute value of y is less than or equal to 1. Just another way to write interval notation. Tangent and cotangent, we found that the range was all real numbers. We wrote it like this. In interval notation, that would be to -infinity, from -infinity to +infinity, parentheses, not brackets. And in set notation, that would be read all y such that y is a real number. Secant and cosecant, we found that their ranges had that jump, that gap in between +1 and -1. So interval notation, this is the way we wrote it. Set builder notation would be all y such that the absolute value of y is greater than or equal to 1. All right, we are given a task here, an example here. It says, is each statement possible or impossible? Use the range to decide. So we're being asked if sine of any angle, theta, could be equal to 2.5. Well, when you're asked a question like this, make sure you refer to the range. We know that sine goes up to +1, down to -1, like bounces in between +1 and -1, but it never goes above or below that. So it couldn't get to this height or this value of 2.5. So that would be impossible. Reason, 2.5 is outside the range of the interval -1 to +1 inclusive. All right, next one. Could tangent of theta be equal to 110.47? Well, we look at the range, and the range on tangent is all real numbers. It increases like this, if you recall. So yeah, this could, there are no holes or gaps, so this could get to a height or a value of 110.47. Goes all the way up to some concept of infinity, so it can certainly get to 110.47. So we would say that this is possible. One justification would be tangent can be any real number value. All right, one more. Go ahead and pause the video and you try this one about secant. All right, welcome back. Let's see what you wrote. If you said impossible, you got it right. Justification, negative 0.6 is not in the range. If you're not sure where that came from, you want to look at the range on secant. So we go up here. The range on secant is negative infinity to negative 1, but then there's that jump where it doesn't exist. And this value of negative 0.6 would be in this empty part right here. Therefore, secant of theta could never be negative 0.6 because it does not exist between negative 1 and positive 1. If the quadrant of the terminal side of theta in standard position is known, then the signs of the 6 trig functions can be determined by using what I'm going to show you right here. Okay, quadrant 1, all functions are positive. In quadrant 2, only sine and cosecant are positive, the other 4 are negative. In quadrant 3, tangent and cotangent are positive, the other 4 are negative. And in quadrant 4, cosine and secant are positive, the other 4 are negative. Now if you're thinking, whoa, that was a lot of information, where'd that come from? Turn back to your graphs. Quadrant 1, that is from here to here. So we can see that sine is above the x-axis and therefore it's positive. Quadrant 1, from here to here. Cosine is positive because it's above the x-axis, okay? All right, secant, first quadrant is here, and that is all above the x-axis, so it's positive. Secant in quadrant 1, above the x-axis. Tangent in quadrant 1, go from the origin. And cotangent in quadrant 1, also positive here. All 6 functions are above the x-axis in quadrant 1. That is why we wrote this here. Quadrant 1, all functions are positive. Let's check out quadrant 2. It says that sine and cosecant are positive, meaning that the other 4 are negative. Let's go check that out on the graphs. Okay, quadrant 2, sine is still above the x-axis, so still positive. Cosine drops below the x-axis, so it's negative. Cosecant above the x-axis, in quadrant 2 it's positive. Secant in quadrant 2 below the x-axis, so it's negative. Tangent in quadrant 2, we are below the x-axis, so it's negative. And cotangent in quadrant 2, here, below the x-axis. So in quadrant 2, we can see that only sine and its reciprocal function cosecant are positive. The other 4 functions are negative. And that is what it means by this statement here. Quadrant 2, sine and its reciprocal function cosecant are positive. The other 4 are negative. You can look at your graphs and do what we just did for quadrant 3 and quadrant 4. I want to show you something someone made up to help us as trigonometry students remember this. It looks like this. And when I first saw it, it was read all, okay? A for all. A for what? That's right, A for all. And then we head to quadrant 2, okay, it's counterclockwise. This S we read as students, so all students. Then we travel here. This T we read as take, so all students take. And this is C for calculus. So all students take calculus is one way that someone made up that has turned out to be very useful to help us remember that in quadrant 1, all functions are positive. In quadrant 2, S or sine and its reciprocal function cosecant are the only positive ones. In quadrant 3, take, So tangent and its reciprocal function, cotangent, are the only positive ones. All other four are negative. And C for calculus reminds us or helps us remember that cosine and its reciprocal function, secant, are the only ones positive in quadrant 4. The other four functions are negative. Okay, so after that lengthy explanation of all students take calculus, let's see if it'll help us through these examples. Are the 6 trigonometric functions of theta equals negative 200 degrees, positive or negative? All right, well, negative 200 degrees, I'm going to sketch that angle in standard position, opens in the negative direction, okay? Don't accidentally go this way 200 degrees. The negative represents the terminal side opening in the negative direction. So through quadrant 4, so it would go to, we're at 90, negative 90, considering the direction. Now we're at 180, so a little bit past that, just 20 more degrees past that. So our terminal side would be here. So this is an angle measure of negative for direction and 200 degrees for its measure. And it lands in which quadrant? If you said quadrant 2, you got it right. Okay, so let's reread the question now. Are the 6 trigonometric functions, I'm going to change this to in quadrant 2, positive or negative? All right, so we go over here to quadrant 2, all students. So S for students means sine and cosecant. Those are the only ones that are positive. The other 4 are negative. So we can write it up like this. Negative 200 degrees is in quadrant 2. Sine and cosecant are positive, and the other 4 are negative. All right, let's try one more. It says, which quadrant is sine of theta greater than 0 and tangent of theta less than 0? I'm just going to restate that slightly as which quadrant is sine, instead of greater than 0, I'm going to write positive, and tangent of theta, instead of less than 0, I'm going to write negative. So now my question reads, what quadrant is sine positive and tangent negative? Okay, I'm going to erase a lot of this stuff. Okay, so we're being asked to identify the quadrant. So our answer is going to be either quadrant 1, quadrant 2, quadrant 3, or quadrant 4. Okay, I'm going to address the first restriction or requirement, and that is that sine needs to be positive. Okay, if sine must be positive, quadrant 1 is an option, quadrant 2 is an option, quadrant 3 is not. For sine to be positive, we would have to be in quadrant 1 or quadrant 2, because in quadrant 3, sine is negative, and in quadrant 4, sine is negative. So I suggest in your exercises in My Lab and Mastering, you go through these one by one like I've done here. So now my answer is narrowed down from the 4 quadrants to 2 options left, okay? It cannot be either of these. These do not meet the first requirement, regardless of what this second requirement says, because it says sine has to be positive and tangent has to be negative, not or. So these are out. All right, now let's check of the 2 remaining where tangent is negative. Okay, in quadrant 1, all functions are positive. So tangent is positive there. So quadrant 1 is out. And in quadrant 2, sine and cosecant are positive, which leaves the other 4 to be negative. That meets our second requirement, tangent of theta being negative. So the answer is quadrant 2. One way to write that up would be sine is positive in quadrant 1 and quadrant 2. Tangent is negative in quadrant 2 and quadrant 4. Both conditions are met only in quadrant 2. For all angles theta for which the function values are defined, the following identities holds. The reciprocal identities, which we've talked about these before, you guys. This is nothing new. I hope you're not staring at that like, whoa, that's a bunch of new stuff. You know these. The reciprocal of sine is cosecant. Written up as an identity though, it would read sine of theta is equal to 1 over cosecant of theta. Reciprocal identity, cosine theta is equal to 1 over secant theta. Tangent of theta is equal to 1 over cotangent theta. And this second row here, cosecant of theta is equal to 1 over sine. Secant is equal to 1 over cosine. And cotangent is equal to 1 over tangent. These are called the reciprocal identities, which you know these. We've been working with these since the very first video. Next set of identities are called the Pythagorean identities, which again, we've talked about the Pythagorean theorem. So don't let this appear to be something brand new. You know this stuff. It's just now we're in trigonometric identity form. So instead of, let's say what we were used to when we first learned the Pythagorean theorem, which is that one leg of a right triangle squared plus another leg of the right triangle squared is equivalent to the length of the hypotenuse of that right triangle squared. Okay, but for our Pythagorean identity with trigonomic functions, A would be sine of theta and B would be cosine of theta. Those are the x and y coordinates, and 1 comes from the unit circle, has a radius of 1, and 1 squared is 1. So this right here, no problem. It's just like the Pythagorean theorem. This one also holds true. Tangent squared theta plus 1 is equivalent to secant squared theta. And last one, 1 plus cotangent squared theta is equivalent to cosecant squared theta. Last set of identities here are the quotient identities. Tangent of theta is equivalent to sine of theta over cosine of theta. Well, if we look at all of this in terms of x, y, and r, it would go like this. Tangent of theta in terms of x, y, and r is y over x. Okay, so that's our tangent theta. Then there's an equal sign. Numerator on the other side of the equal sign is sine of theta. And we know that sine of theta in terms of x, y, and r is y over r over denominator on the other side of the equal sign is cosine of theta, which we know cosine of theta in terms of x, y, and r is x over r. And so the left side of our equal sign is equal to the right side of our equal sign. Whatever the radius is, it would cancel out here and here. Those look like x's. Let me scribble them out like this, and we can see that the left side of the equation is equal to the right side of the equation, making this identity called the quotient identity. Tangent's reciprocal function is cotangent. So if you take the reciprocal, sine over cosine, take the reciprocal to be cosine over sine, you have the second quotient identity. All right, you guys, these are called the fundamental identities. They're the first ones we work with in trigonometry. They're the ones you're going to want to know. I don't want to say memorized, but if you think about them, you should be able to come up with them pretty quickly. That's going to save you a lot of time as you go through the exercises. Let's see some exercises in which we can use those identities. Use identities to find sine of theta and tangent of theta, given that cosine of theta is equal to negative radical 3 over 4, and sine of theta is greater than 0. Okay, so what I like to do is list what we have, okay? What tools do we have? What values do we know? Okay, well, we have cosine, and that's the only value we know. We know sine is greater than 0, so positive, but we don't know its value yet, so I don't want to put that in the tools that we have yet. Now I like to write, what do we need? What is the question asking us to find? All right, well, the question is asking us to find sine and tangent. So I'm going to pick one at a time, okay? I'm not going to try to get both of these at the same time. Just pick one. So I'm going to try to find sine. All right, doing this helps me strategize on which identity might help me. If I have cosine and I need sine, I'm going to go back to my list of identities and I'm going to pick one that is dependent on cosine and sine, and hopefully nothing else. So let's look at our list of identities. Can you guys find one here that has sine and cosine and no other trig functions involved? If you went with the first Pythagorean identity, you got it right. This identity has sine and cosine and no other variables, no other trig functions, no other unknowns. What that does for us is allows us to plug in our known value for cosine and then use our algebra skills to solve for sine. All of that thought process has to be done before we can start writing our solution. So put yourself through that thought process, which is list what you have, list what you need, turn to your slide of identities and pick one that will work for you. Then we write that identity in its general form first. This is a good habit. Someone has taken, many people, probably a team of people, have taken the time to prove this identity. The least we can do is write it down in its general form so that we help avoid misusing it. Okay, we're going to take it from its general form and plug in what we know. So cosine of theta was the one that we know. We were told that its value is negative radical 3 over 4. So we take cosine of theta, change it to negative radical 3 over 4. Notice that the squared is on the outside here, okay? Outside. Make sure also that you're writing a complete sentence from left to right on your next line. That would be rewriting sine of theta. Rewrite the plus sign. Don't rewrite cosine squared theta. Write it in a form that we know. Rewrite the equal sign, rewrite the 1. Complete sentence from left to right. These habits will really pay off when you're trying to manipulate an equation that has a trigonomic function. Okay, from here, our goal is to isolate sine of theta. Okay, our goal is to find sine of theta. So we want to isolate this piece right here. I want to show you this exact same equation, but take the sine theta and change it into just, I'm going to change it into a question mark, okay? Same thing. So I'm going to take sine theta, change it into a question mark. Then there is a squared. Then there is a plus sign. Then there is an open parentheses, a negative radical 3 over 4. Then there is a closed parentheses, a squared, an equal sign, and a 1. All right, the reason I'm showing you this is because this equation right here with the sine theta showing might seem a little bit intimidating compared to the way you would have seen it in your algebra class before trigonomic functions would have looked like this. Well, actually in algebra class it probably would have been an X, not a question mark. So I'll change that. Let's erase our question mark and change it to an X so it looks very similar to a question you would have seen in your algebra class. Had you been given a question in algebra that said solve, you would have taken this equation right here and manipulated it, moved everything around until you isolated X. So let's see, to isolate X, well, I want to do this squaring first and then I'm going to move it to the other side of the equal sign. So I would have my X squared plus Negative times negative is positive. Radical 3 times radical 3 is 3. 4 times 4 is 16. That equals 1. Next thing we would do in our algebra class to isolate x would be to subtract the 3/16 from this side of the equal sign and this side of the equal sign here. That would leave us with x squared equals some value. It would be whatever 1 minus 3/16 is. Let's think, common denominator, that'd be 16/16 minus 3/16. So that would be x squared equals 16 minus 3 is 13/16. And then our last move would be to get rid of the squared by square rooting both sides of the equal sign. Square rooting both sides would isolate our x for us, as well as we're introducing the square root here, so we need to address the positive and the negative roots of radical 13 over 16. Okay, sign can be positive or negative, so we would need to address both of these roots. Positive radical 13 over, let me just take this one step further, positive radical 13 over square root of 16 is 4. I wanted to simplify that there. Or the negative root of radical 13 over 4. We'd have to consider both, and we're actually going to address which one to choose by this restriction way up here a long time ago when we read it. It says, and sine of theta has to be greater than 0. So we're going to choose the positive root, which is x equals radical 13. We don't have to write the positive. If it's not there, it's implied. X equals radical 13 over 4, which means our sine theta equals radical 13 over 4. Okay, so if this were algebra class, this is what it would look like. You would get through it. It may not be easy, but you would do it. Okay, you all passed your algebra classes. That's how we get our prerequisite skills for a trigonometry class. So we're going to do the same thing now. It's just instead of the x, it's going to be a sine theta. So the next line would look like this. Sine squared theta equals 13 over 16. That's right here. Next line would look like this. The square root of theta is equal to plus or minus the square root of radical 13 over 4. And finally, we would choose the positive root, choose the positive square root since sine of theta has to be greater than 0. And we have our answer of sine theta equals positive radical 13 over 4. Let me erase the algebra part so you can see it. I'll erase one more line there. Okay, so if you ever need to do this, work it out as an x so you can get through your algebra, do it. It's worth the time. But what I want to do now is erase all of that so you can see what the solution will look like when you start to feel comfortable going straight to isolating sine theta in an equation. Solution would look like that there. Now we're going to do the second part of the question, which is to find tangent of theta. So we're going to put ourselves through that thought process again, where we list what we have and what we need. Okay, so over here we have cosine, and now we have sine. We found it. So sine moves to this side. And what we need is requested of us in the problem, tangent of theta. Okay, so we need to look at our list of identities. We want to find one that has sine and cosine. These are fine. They can have sine, and the identity can have sine and cosine because we know their values, but it needs to have tangent in it as well. So it can have tangent and cosine, or just tangent and sine, or it can have tangent, sine, and cosine, but it must have tangent, otherwise we can't solve for it. And it could have cosine or sine because we know both of those values. Okay, back to the identity slide. And I'm going to start erasing this annotation. I want you guys to look for an identity that will help us with the second part of that question. Did you pick one yet? All right, if you picked the quotient identity, sine of theta over cosine of theta equals tangent of theta, good choice. Let's just go through and check sine. This reciprocal identity, it's out because it has cosecant. This one's out because it has secant. This one is out because it has cotangent. This one is out, well, for multiple reasons. It doesn't even have tangent. If we're trying to find tangent, it has to be one that has tangent. This has tangent, but it also has cotangent, which we don't know. So we're going to try to avoid it. This one doesn't have tangent at all. Don't use it. This one has tangent, but it also has secant, so we're going to try to avoid it. This one, tangent's not there, and this one, tangent's not there. So I'm not saying these are the ones that have tangent are completely out, but you want to try to find one that has tangent and only variables that you know. For example, if somebody picked this one, that is also a good choice. Even though we don't know secant, we know its reciprocal identity cosine. So you could use this one, making it 1 over cosine instead of secant if you want to, okay? But I'm gonna go with this quotient identity. It's the most direct choice for our identities. So remember, it takes all of that thought process before you can even start to write your solution. Put yourself through that process, which is, again, list what you have, list what you need, pick an identity that will help you. Then write the identity in its general form, like you see here. Plug in the values that we know. Okay, this looks like a lot, I know, but it's okay. All we did here was take sine of theta and we changed it to its known value of radical 13 over 4. And we took cosine of theta and we changed it to its known value of negative radical 3 over 4. Positive divided by negative is a negative. And the 4's canceled out, leaving us with negative radical 13 over radical 3. And technically, we have done what we were asked to do, which was to find the value of tangent. It is negative radical 13 over radical 3. However, this next step is called rationalizing the denominator. This is not trigonometry work right here. This is just algebra. So we're just going to multiply top and bottom by radical 3 to get the radical out of the denominator, bringing us to negative radical 39 over 3. So this right here is considered more simplified than this one because it doesn't have a radical in the denominator. So we would write our answer as tangent of theta is equal to negative radical 39 over 3. And what we have just done is used identities to find unknown trig function values. We have one more slide and we are done with chapter 1. All right, here we go. Last slide for chapter 1. Use identities to find sine and cosine given tangent is 4/3 and theta is in quadrant 3. I'm going to list what we have and what we need. So we have tangent of theta, it's 4 over 3. And what we need is sine and cosine. I'm going to write them both down, even though I'm not sure which one I'm going to go for first. Okay, we have tangent, we need these two. Let's look at our identity list. So I'm looking through for something with tangent and sine, or for something with tangent and cosine. There is no identity here that includes just tangent and sine, and there's no identity here that includes just tangent and cosine. So we're going to have to do a two-step identity process. I'm going to show you the ones that I chose first. I was thinking about this Pythagorean identity and how it has tangent, which we know, and it has secant, which is not what we need, but I know that secant is the reciprocal identity of cosine. So I think if we use this first to find secant and this one second to find sine, we should be good. There are other options there. If you came up with something different, go with it. Try it. Worst case, you got it wrong, and just put that solution aside, start fresh, and try again. All right, so let's see what the solution would look like using this identity first and this, well, or this actually, identity second. One of these two, they're the same. All right, first just another note on the information that theta is in quadrant 3. That would be sine and cosine. They're both negative in quadrant 3. So whatever our answers are, we want to make sure that we're choosing the negative for sine of theta, and our answer for cosine of theta should be negative. That's what that helps us out with. All right, here we go. Let's use the identity that I selected to be first, tangent squared theta plus 1 equals secant squared theta, to find secant of theta. So we're going to replace tangent of theta right here with its known value, 4/3. That looks like this, 4/3. Notice that the squared is outside the parentheses. Then we have plus 1 equals secant squared theta. This equation right here, we're going to manipulate until we isolate secant of theta. So I'll start by squaring the 4/3. That would become 16/9, and then adding 1 to that. 16/9 plus 1. Well, with a common denominator, that would be 16/9, and instead of writing it as 1, we would write it as 9/9. That would be the 25/9 that we see here. Okay, so we have squared and we have added. Next thing we need to do to isolate secant is to get rid of this squared right here. We do so by square rooting both sides of the equal sign. The square root of 25 is 5, and the square root of 9 is 3. And I chose the negative root because we were told that we're in quadrant 3, and secant of theta is negative in quadrant 3. Okay, now if we use our second identity, which is that reciprocal, that was secant of theta is equal to 1 cosine of theta. Plugging in our negative 5/3 for secant being equal to 1 cosine, and it's just going to be the reciprocal of our negative 5/3. So it's going to be negative 3/5. So our answer is cosine of theta equals negative 3/5, and that was using the reciprocal identity. All right, that is the end of chapter 1. Thank you guys for being here. At this time, I want you to finish your chapter 1 homework, which is the remaining problems, which you should be picking it back up from question 39 and all the way through to the end, which I believe is number 48. So get all of your chapter 1 homework finished before you move to our videos on chapter 2. My name is Jami Emigh. Thank you for being here, and I'll see you guys next time.